In today's lesson, we're going to look at finding the areas of 5 different types of polygons. We've got the triangle, parallelogram, trapezoid, rhombus, and kite. Now, a lot of these you have found the areas of before. You might even remember what the formula for finding the areas are. But before we get into some examples, it's really important with anything that we do in math that we don't just accept and work through a problem and just memorize it, but actually understand it, especially for something like this that is concrete and we can see why the area formulas are the way they are. This is an activity that you may not be able to replicate at home, so I would just watch for each one of these examples and just kind of verify in your head, oh, okay, that makes sense why that formula is the way it is, and then when it comes time to write down the formula, you can write that into your notes. So we are starting with the parallelogram, but first, just what we're looking at here, we've got several rectangles that are all the same. We're going to be looking at each one of them for a different shape, but each rectangle is an 11 by 5. And we're just using the little boxes here to count. Those are our units. So our length and our width is an 11 by 5. So that means that for a rectangle, hopefully we remember that the area of a rectangle is base times height. So the area of the rectangle is going to be 55 units squared. Okay, so that could come into play when we're comparing it to another shape and kind of seeing how they compare, what the formula might look like compared to the formula of a rectangle. So we're going to start with this parallelogram. And notice that for this parallelogram, the base of it is the same as the base of the rectangle. So the base is 11. And then it also has a height of 5. Okay, so they have the same dimensions, even though the parallelogram is like squished off to one side, they actually do have the same dimensions. So what I want you to see here is that if we take our parallelogram and we cut it along the height, the parallelogram actually has the exact same, and this isn't going to be perfect because I cut it out, but it should have the exact same area as the rectangle because the area of a parallelogram is found the exact same way by taking the base times the height. So for our first formula here, your parallelogram area is going to be base times height, just like the rectangle. So for the triangle, I've got 2 different triangles to look at. We've got one that is a right triangle. And notice that for this one, it has the same dimensions as our rectangle. It has a base of 11 and a height of 5. And notice that its area is exactly half of the area of the rectangle. So that's important. But I also want you to look at a different type of triangle. So notice that this one also has that base of 11 and a height of 5. So it doesn't matter what kind of triangle it is, as long as it has that same base and height, we know that the area of the triangle should be half that of the area of a rectangle that has the same dimensions. So our triangle is going to take up half of the space, and that is because the area for a triangle is 1/2 base times height. Which brings us to the trapezoid. And for the trapezoid that I have here, neither of these bases are the length of the rectangle, but I can use the boxes up here to just kind of estimate. It looks like the top base is about 8. And then the bottom base, let's see, this was 11, so about 14. Okay. The height is the same as the height of the rectangle, so we've got a height of 5. And then if we remember from working with quadrilaterals, also with triangles, that the mid segment of this trapezoid is that segment that goes from the midpoint of one side to the midpoint of the other side. And just estimating that, it looks like that length is about the same as the rectangle, and it is intended to be. So our mid segment ends up being that 11. Notice that this area is similar to the rectangle. In fact, if we rearrange our pieces here, we're going to see that their areas are the same. Oop, not quite. Okay, so if this trapezoid has an area of 55 units squared, just like our rectangle, what lengths here are we multiplying together? We've got the height and the mid-segment are 5 and 11. If we remember back to when we learned about mid-segments, we might remember that they are calculated by taking the average of the bases. So if I took the average of 8 and 14, so I'm just going to write this down here. 8 and 14 divided by 2, or just my mid-segment is that 1/2 base 1 plus base 2. And I would get 22 over 2, which is 11. Okay, so what that means is that we're taking 1/2 base 1 plus base 2 times the height, and that's where the formula for the area of a trapezoid comes from. It is really just mid-segment times height, but that's harder for us to remember. So instead of saying mid-segment, we're going to say 1/2 base 1 plus base 2 times the height. But this whole part of it is really just talking about the mid-segment. The kite is probably something that you have not found the area of before. So we've got some different dimensions to look at. It looks like one side length is about 8. The other side length is about 4. And then we're also going to look at the diagonals. That our long diagonal is about 11. It doesn't matter which one's which, by the way. And the other diagonal is about 5. Okay, so again, just like on the last one, trying to pick out those pieces that are relating back to the rectangle. This 11 and 5 is what we should focus on, those diagonals. But this kite doesn't look like it's quite the area of the rectangle. So let's see if we can figure out how they relate. I'm going to cut our kite in half as best I can. That wasn't too great. And I'm also going to cut it right here. Okay, so let's see if we can fill in our puzzle. That little piece there. Okay, so by rearranging this, we should see that the area of our kite is about half the area of the rectangle. Which leads us to believe that if I'm finding the area of a kite, that I should be taking 1/2 of the diagonal times the other diagonal. So for our kite, our area is going to be 1/2 diagonal 1 times diagonal 2. And it doesn't matter which diagonal is which, just the fact that we're multiplying by both diagonals. Our last polygon for the day is the rhombus. And hopefully we remember from our quadrilaterals unit that a rhombus is just a type of parallelogram. So actually the same formula that we use for a parallelogram could work for the rhombus if we have the right information. So if we have the base and the height, then yes, we can go ahead and find the area the same way that we do for a parallelogram. Our rhombus is also a parallelogram, but we do have a different way that we can find the area of a rhombus. So 2 different formulas. So I do want to look at, here's our rhombus. Remember, all of its side lengths should be the same if it's a rhombus, and it looks like our side length is about, let's see, 3, 6, 7, somewhere in there. But then we're also going to look at the diagonals, and we've got one diagonal that is 11, and then the other diagonal is 5. So kind of the same thing that happened with the kite is going to be happening here with the rhombus. If I want to confirm that, I can rearrange my pieces here to see if the same thing that happened with the kite is going to happen with the rhombus as well. Sorry, I'm trying to be fast here. It's not really working out. Okay, and we see that it does work out the same way. So just like our kite, how it had 1/2 the diagonal 1 times diagonal 2, that also works for the rhombus. This is kind of interesting because the rhombus is actually a parallelogram, but it has something to do with their diagonals. If you remember that the rhombus and the kite both have diagonals that are perpendicular to each other. So because those diagonals are perpendicular, that's what allows us to find the area this way as well. So for the rhombus, we've got our two different areas. We've got our base times height. If we're given both of those, we can use base times height. If not, we could also use 1/2 diagonal 1 times diagonal 2, just like the kite. Before we get too far in our lesson, a public service announcement. When you're finding the height of an object, it must be done a certain way. For instance, if I measure the height of my cup like this, I would say that it is 12 inches tall. Does that make any sense? No. How I have to measure my cup is by having whatever I'm using to measure it perpendicular to the base of that object, and that's what allows me to be accurate when I'm measuring the height of something. The same logic applies to polygons. So if I'm trying to choose the base and height of a parallelogram in order to use the area formula, I want to choose the height that is perpendicular to the base, even if it's not a side of the figure. So in this example, 10 would be the base, and then the only length that we have that is perpendicular to that base is 7. So 8 would not be the height. This would be like measuring that parallelogram by taking a slant up to it. For triangles, sometimes this means that our height of the figure is even outside of the figure itself. And that's okay. It just has to be perpendicular to the base.